I'm Terry Goodman from Intech Solutions down here in Sydney, Australia. I'm going to present on data quality, specifically for identity resolution in a graph database. So I'm going to roll right into it. So firstly, what's in my presentation? Firstly, I'll introduce data quality and entity resolution by definition and define what I mean by those terms. Then we'll talk about graph schemas designed specifically for identity resolution, and we'll explore various schemas. We'll talk about transforming data in an optimized manner to match those schemas. We'll talk about what sort of enhancements can be done to the data specifically for identity resolution. And we'll talk about identity resolution algorithms within a graph that can be done. And then we'll move into questions. So firstly, to define what I mean by identity resolution. So in simple terms, identity resolution is actually a matching process to identify unique entities, typically person, to link information in order to avoid duplicates and to expose a complete information about each entity. So, for example, in a kind of simple scenario, you have a customer who places an order, and then later on you get another record of a customer making a payment. In that scenario, entity resolution is trying to identify that it's actually the same customer who made the payment for their order. So a simple example of where failure to recognize that it's the same customer could lead to problems, and the entity is hence resolved to a single customer. So that's fundamentally what I mean by entity resolution. Data quality, on the other hand, is a bit more generic, and I'm talking about parsing, standardizing, and validating, as well as appending information enhancements. So reasonably broad definition of data quality. We're talking about classifying data, about placing data elements in their correct fields, invalidating or repairing elements of data, in bringing data to a standard format. So when we do our entity resolution, we can compare like for like. Example of name processing. So here's a simple example just to illustrate what I mean. So your input might be a name, but as we can see here in this instance, it's actually got two people's names embedded in the one field, which presents a data quality problem. But that can be resolved by parsing the data into discrete fields. And I'll bring your attention here specifically to, firstly, that we recognize the first person. Scroll back there. Being John Smith, first name, last name. We've also got a bit of an enhancement going on here with a gender assignment. So we know that typically a name of John is a male, and typically a name of Joanne or Joan is a female. And more importantly, we've recognized that there's two people, probably related people, in this record. So how do we optimize a schema in a graph sense? So firstly, I'll talk about various types of schemas. So firstly, a person vertex with identifying attributes stored as attributes. So in this scenario, we have a customer, and we're in effect storing the customer's name, phone number, email, location, all against their customer vertex. If we have two such customers, we can match these, and if they're identical, then we can identify them and merge into one. However, very often we have different representations of the customer's name, phone, email, and we can identify that they are similar, but when we load the data, they're not necessarily linked, which is can be problematic. So how do we resolve that? So in this particular scenario, the payment is not recognized and linked to the order. A person vertex with identifying attributes stored as vertexes. So what we do in this instance is we, in effect, trim down our customer vertex, and we pull the name, phone, email, and location out into their own vertices so that each of them can then be linked to this customer in scenarios where they're the same. And I'll probably just illustrate that by example. But in this instance, immediately you can see, assuming this customer 1 and customer 2 have the same name and location, we've immediately linked them together, albeit we haven't established that they're necessarily the same person. So what's the effect of attributes breakdown? So let's give an example that's actually got real data. So shifting information from the attributes to the vertices. So let's take a particular record, customer 1, who has a preferred name of William Jewell, customer 2, who has a name of Bill Jewell, so slightly different, but shared phone number and a different email address. So in this particular example, we can see that I've connected the customer through the phone, but again, we haven't established that they aren't the same customer, but I have connected them. So by purely bringing the data into a graph structure and separating the attributes into vertices, I've been able to link them so that these are now connected records. The link between customer 1 and customer 2 is easily exposed in the scenario just by shifting into this graph data model. But we don't yet know that customer 1 actually is customer 2. It's the same person. So how can we progress that a little further? So parsing the data for better linking. So what do I mean by parsing? Let's explain. So customer 1, same record as before. They have this name and they have that email address. Now what we want to do is actually break down the name and the email address further by applying parsing. So this name, William Jewell, we apply a parsing process to it. We identify that the first name is William, the last name, surname is Jewell, which I can clearly see by visual inspection. But more interestingly, I can also enhance the data by appending Bill, because my parsing engine is intelligent enough to know that a lot of Williams actually call themselves Bill. So at least in Australia they do, and I believe in America and other countries in the world that's common as well. So appending the alias, we're now able to get richer information. The email address can also be parsed to a username and a domain name. So we can then now have a look at the attributes on this side of the equation over there and see how do they link. So we break our data further. Parsing an email is a simple thing and can be done just straight within any coding or scripting language. But parsing a name or an address typically requires something more sophisticated in terms of your parsing. And we use IQ Office, which is our product to do that, which is called directly from Tiger Graph or as part of the data pipeline. Example of a more sophisticated example of parsing. So let's say your name is a whole big long string. Now this particular name is typical in the banking world for account names. So someone might open up an account and call their account John and Joan Smith as trustee for Intex Solutions, Pty Limited, trading as Data Quality Gurus. Whole big long string, but it's not that uncommon. Now, by parsing this data, I can process that single string to produce a parsed broken out string. And we can look at this in a bit more detail. So the first thing to recognize is to classify the data. So we can classify that this is an organization. We can break out the name. So the first person here is John Smith. There's a second person, Joan Smith. There's a company, Intech Solutions. There's another organization name called Data Quality Gurus. And the really important thing here is we now have some relationships established just being extracted from the string. And that's a as trustee for relationship between individual 1 and individual 2 to organization 1. So that is John Smith and Joan Smith are both joint trustees for Intech Solutions. We also have a relationship with trading as, also extracted from the string to indicate that Intech Solutions is trading as Data Quality Gurus. Of course, not actually true in this instance, the sample data, but we're able to pull this data out from free format string and really enrich the graph so that we can identity match on John Smith and Joan Smith, and we can also expose relationships within our graph. So a very important concept when we talk about identity resolution and exposing complete information about Intech Solutions or about John Smith, we can now match these entities. So looking at it in terms of a graph, with richer parsed data, we can further break down the vertices. So in a graph sense, what does it look like? So we can now identify that the first name is actually William. I have another record where I've got the first name is actually Bill. The surname is Jewel. So these agree exactly. And I also have an alias relationship between William and Bill. Now, all this is extracted from the parsing. In my previous example, we only matched on phone. And now we're matching substantially on the name as well. So we're able to better resolve this identity. Now, the email address, we've parsed that. Now, very common, people use a same or similar username for their email, but they may also have multiple email providers, a work email, a personal email, and often share a similar username. So by breaking down the username and comparing it separately, I'm able to find another point to link the data. And in this particular example, the user used outlook.com for their one email address, and they used Gmail for the other email address, but used the same username, which might be a coincidence, but when you add the balance of probability of all the other attributes of data, we actually have quite a strong connection between these customers, probably indicating that they're the same person. So now all I've spoken about so far is fields of data matching exactly and parsing that data in order to resolve connections. Now we can and actually do take it one step further, and we look at similarity. So similarity typically caters for misspellings and other various data anomalies, typically in a matching process. I'm going to define two different types of similarity, the one being attribute similarity, when we're looking at a single attribute of information to say how similar they are. So in this instance, I can compare this full string, William Jewell and Bill Jewell, and do a similarity algorithm on it. In this instance, I'm actually using a gyro similarity, but there are multiple other similarities and similarity libraries that we provide and can readily available and callable from TigerGraph. So scoring the similarity of these two strings, we get 87% similarity, which I must admit is higher than I actually expected. Comparing William to Bill, we get a slightly lower similarity, but still, if we look at this Bill, it's actually just one letter out. So of these 4 letters, 3 of them are contained in this string. And the emails also produce a reasonably high gyro similarity. Now, record similarity is a little different. So what we're talking about is taking a customer and another customer and taking all the information that we have about them and trying to establish what's the aggregate similarity. So in other words, how similar is this customer from this customer? Now, this concept of similarity is not only relevant for identity resolution, but it's relevant for detecting all sorts of patterns in your data. So it goes way beyond identity resolution, but I'm going to stick to my topic, which is identity resolution for customer 360 scenarios. Now, how do we actually calculate the record similarity? At the end of the day, that's the Nevada. That's our endpoint that we're trying to achieve. So one method is we fully parse out the data and create all the fields separately, and we match them and add the similarity scores as edges connecting one field to another where they're not identical, but they are similar. So for example, here I've got William to Liam with a similarity of 43. I have a date of birth here, and I'll just point out this little subtle difference. The 0607 is traversed here. So here I've got, actually no, it's the same. What I meant to say, in a scenario, if the day and month were traversed, we would have a similarity rather than an exact match. Looking at a phone number, this phone number, I'll just go back a little. This phone number over here ends with 00. This ends with 12. In reality, this is my direct phone number, and this is a landline for the switch. So we would classify them as similar. So just go back to there. Now, so how do we actually calculate the aggregate score of this customer, how similar they are to this customer? That's where we apply various options of algorithms where we traverse all these links, adding up the scores as we go according to an algorithm that we choose. So we might choose to apply a certain amount of points, if you like, for the surname agreeing. We might apply some points for the first name being a little bit similar, and so on until we get an aggregate score, which will indicate the accumulated record similarity. Now, the exact algorithm that you use, there's actually standard algorithms for it, or you can code your own. In a scenario where we use a standard algorithm, one example is to call an external library, such as the ArcGIS software that has a probabilistic matching engine attached to it, where we pass in all the data linked to customer 1 and customer 2, and we get back the probabilistic match score. Sounds simple. And to use, it actually is simple. So in this scenario, we haven't necessarily calculated the similarity of each field because we don't need to. That's done externally by the library. The library will take as input all this data, effectively what I've got on screen, run a probabilistic algorithm, and return a probabilistic record matching score between customer 1 and customer 2. Now, that score can be used to either create a similarity vertex that you store in your data that directly connects customer 1 to customer 2 with a certain similarity. In this example, that similarity is sitting around 73. Or it can be done in real time on the fly without necessarily pre-populating or creating edges between customer 1 and customer 2. Now, probabilistic matching engine, I'll talk a little bit more about that. So the ArcGIS library can be called directly from within TigerGraph. So within TigerGraph, you can call external functions. You can embed them. You can create your own C code, which operates at a very high performance. And you could use that directly within TigerGraph. It applies a system of points and penalties based on how similar your various attributes are. And if they are sufficiently similar, then it will give a positive score. If they are too low, so in other words, their similarity is below a threshold, will actually penalize it, that particular attribute. So if I go back to the example I had before, the fact that Gmail and Outlook are different domains, it would actually get a bit of a penalty. But the fact that the username is the same would get a positive score. And the algorithm dictates how many points to give it or to take away in order to result to a true probabilistic match. Now, when we compare each of the fields, we have extensive ways of comparing fields and extensive ways of defining what we mean by tolerance. So a tolerance might be an algorithm such as Jaro or Jaro-Winkler, which will dictate how similar two strings are. That's good for names, but something like a date of birth, you'd want a very different kind of tolerance, because taking one character in or out isn't indicative of real world problems. With dates of birth, what I've noticed is a lot of people do in fact write the month, day, the wrong way around. Different countries represent that differently. So that's a common error in collecting data. And that can be catered for in tolerances that are specifically geared to identify that. So as you can see here, there's a lot of different tolerances here that can be used, and we define the tolerances different for each type of comparison. It will also take into account how common each value is. So for example, if I've got an uncommon name or a common name, these will get different scores. So for example, if I've got a name like that, Agnesa, matching to Agnesa, this is an uncommon name, at least in Australia, and I suspect the US as well, and hence it gets a high score because there's not much chance that these two names will agree coincidentally. However, if you've got one record says John and another record says John, then the chance of two people being called John coincidentally is actually quite high. John is, I believe, the most common name in Australia. So it gets a much lower score than the field comparison here, even though it's happening on the same field of data. So that probabilistic record scoring really reflects the statistical likelihood of these records being the same person in the real world. So rather than a verbose algorithm that kind of just adds the same amount of points because two things agree, it has a sensitivity for the nature of data in the real world. Looking at another example, and I'm coming towards the end here. So looking at an example from within Tiger Graph of what it looks like. So in this particular example, we've got our two records here, one on the side in green, and another person record here. And we've parsed the data fully to identify that, for example, these two persons have the same street address, they have the same date of birth, they share a surname. The one's Bill, the other's William. But actually we know this person, although his name's William, we know he goes by a nickname of Bill. Also, Bill and William are kind of similar, and the aliases to one another. We can represent that here. And overall, what we can do is traverse all this information and generate a record similarity between these two records to identify with quite a bit of certainty that this record is they're very similar and likely the same person. Now, a lot of this, you may argue, is a lot of noise. And what we're really interested is that this person and this person are the similar or are the same person. And absolutely, we can do that. So we can hide all of that periphery information, or even you can choose to not necessarily generate that in the graph, but do it in the data pipeline, or offline, and yet still populate the graph with a relationship that these two records have this similarity, and we can connect them together. And even through the graph, you could do this and hide all those little attributes of data, and only use them when you need to generate or regenerate similarity scores when more data becomes available. Of course, data is not static, it's continually changing in the real world. So this is pretty much the end of my presentation here. So any questions? Now's your time to raise them. Feel free to be in touch with me after the event. I've placed my email address there for you to see it. And by all means, I'd welcome any questions at any point now or into the future. Gaurav?
Terry, thanks a lot for joining us all the way from Australia. Given that the time zone this time for Graph+AI is not conducive, let me ask you a couple of questions on behalf of the audience, and we will be sure to tee up the questions to you that we receive by chat during the live broadcast of your session. The first question, Terry, is what use cases have you seen in your work at Intech Solutions in terms of combining graph databases with machine learning? Which type of use cases are most relevant for identity resolution that you have seen?
So a lot of the use cases we've seen are in compliance. So that's a lot in government sector. They range from the tax office for tax compliance. They range from, and that goes for the Australian government actually, or doing a lot of this work, and various other forms of compliance. So that's in social services, in healthcare. So a lot of compliance use cases where governments are receiving data from multiple sources and trying to really better understand and gain knowledge of how the various entities that they collect or have information on are related to one another. So in order to do that, they have to quite accurately resolve identities, but not only resolve identities that are the same, but also group identities into groups that act together. So these might be organizations that act together from a tax compliance standpoint, or people that act together and are influenced by things together from a health perspective or tax perspective, or even a criminality perspective. So across the board, we're seeing a lot of use case in government, and also insurance and financial sector. A lot of people are trying to understand better how their customers are related together, and this is a key requirement in order to do that.
Thank you, Terry. My second and final question is about the classic question, which I'm sure you get from your clients also, which is, hey, isn't entity resolution age-old problem? Hasn't it already been solved with multiple pieces of software? Can I just use a relational database to do this, right? So what is the typical...
Yeah, that's a good question. So identity resolution is an age-old problem. So half of your premise is correct. People have been trying to solve this actually since more or less the 70s. So some of the actual matching algorithms that come from the 70s are still commonly used today, and are still very good. So yet I think pretty much everyone I've seen has not actually solved the problem quite yet, and are doing a lot of work to do that. Now, I think the unique thing that Graph brings beyond relational, and I must admit that when I've been doing this entity resolution for 25 years, and I always thought, I can do everything in a relational database. Now I'm looking at it more carefully, and there's a very unique facet to a graph database, and that's that one attribute of connection can be stored in a graph database that can just resolve things. Where in a relational database, you're typically storing things in tables, and these fields are typically all acting together, which means in a relational database, if you've got a customer record, It's built for transactional processing. You've got a customer record. In a relational database, someone will say, okay, is this customer record the same? If it is, merge it. If it's not, don't merge it. But in a graph just gives another window where we can actually recognize that these two records have a shared phone number, have a shared email address, have a shared surname. And this sharing of pieces of information creates connections. And in a relational databases just aren't designed for that. And normally, if you've got two different customers and they're using the same phone number, you're going to store those phone numbers twice. So, almost in every database, and so you should in a relational database. And that is the real reason why a graph database just leans itself forward for not only identifying that two people are the same, but for actually understanding that they are related or connected in some way. So it really is a whole nother dimension of identity resolution, or even just resolving identities and resolving links between identities.
Wonderful. Thanks a lot, Terry. Thank you for joining us at Graph+AI Summit. And we'll be sure everybody can submit their questions through the chat for Terry. We'll be sure to take them back to Terry and copy you on the responses. Thank you.
Okay, thank you very much, Gaurav. And we hope you all enjoy the rest of the show.